Alright, so now we're on to our 1-bit adder from our alu.sim. Arguably the hardest .sim file, but we help a little bit get started with it. So our 1-bit adder, we have 3 inputs and 2 outputs, and a bunch of electricity doesn't really know how to do math, so we kind of have to hard code the answers in. So we just have to cover every single case. So we have 3 inputs, which means there's 8 cases, and we have 2 outputs. The out, and then sum. What's 0 plus 0 plus 0? Well, it's going to be, there's going to be no carry out, and the sum's going to be 0. 0 plus 0 plus 1 is going to be, still won't be a carry out, but there will be, sum will be 1. Now when we have 0, 1's 0, 1, 0, it's still 0 plus 1 plus 0, so it'll still be 0 and 1. Now this is an interesting part. We have 0, 1, 1. Now, we actually can't fit the sum of this into 1 bit, so we have to actually carry out to the next place. If you guys, kind of like when you do 9 plus 1 decimal, we can't really fit 10 into 1 digit, so we actually have to, the sum's actually going to be 0, and we actually carry out that 1 to the next place. It's the same idea here, so carry out be 1, sum will be 0. And then once you fill out this whole truth table, you could do like a simple sum of products. Just have one AND gate for every single case and OR them together. Or you can start using K-maps and try to get a little clever. There's really a lot of freedom what you want to do there. Alright, so moving on to the 8-bit adder. This is definitely the ugliest file you're ever going to make in this entire homework. But we have a 1-bit adder. Let's say you implemented that. You can actually go to your circuits tab and you can start reusing your 1-bit adder. What's a better way to make an 8-bit adder than just putting 8 1-bit adders together? That's what I would do. Not sure if it's too big of a hint, but I think y'all would have found it out. 1, 2, 3, 4, 5, 6, 7, 8. And we can just do, let's do an example. I don't know, some random 8-bit number. 0, 1, 1, 0, 0, 1, 0, 0, 1, 1. And let's kind of see how this interaction works. So, what's 0 plus, and think of it, there's an implied 0 at the carry in, right? For all of these. So, this is 0 plus 0 plus 1. That's going to be, the sum will be 1, and the carry out will be 0. So, when I do this next 1 plus 1, basically an implied 0 plus 1 plus 1, that's going to be 0. I'm going to have to carry out the 1. Notice how the carry out of this place is the carry in of the next place. So, maybe it might be a good idea to change this like that, thing like that. And the sums are basically our final answers in our sum here. So, if you guys remember, we do a splitter here. Make this 8 and 8, paste request, and it told you it's going to be really messy, but you can feel free to move these out. As long as you don't change the name, the autograder should still work. You're going to want these sums, basically these final answers, to be recorded in this final output pin. So that's kind of the general approach here. And of course, you'd have to split these inputs here. It gets really ugly, but hopefully you guys manage. So for the ALUs, I want to introduce you guys something really useful about multiplexers. Now this is an extremely useful tool. I think you're allowed to use the built-in multiplexer. So I like to think of multiplexers as switch statements, right? So it's going to be switch on this selector pin. So let's say I put this function in selector pin. Oh, whoops. I have to make sure my multiplexer selector bits matches. So I like to think about this as a switch statement. on this, whatever you connect to this bottom here. So it's kind of a switch on our func bits. We'll have our case 0, 0. We'll have case 0, 1. Case 1, 0. We'll kind of have a case 1, 1. And I guess imagine this break statements in between them. So if whatever I put here, I can implement a circuit here, and it looks like A plus B, so maybe I could use my adder here. Say I have an adder that maybe you've already made an 8-bit adder up here. I could just put my A and B, this adder. I could send it out, this first blue dot here. And this blue dot is case 0, 0. So if I can implement A plus B, I can feed it into this first body. So these, basically whatever logic you implemented to the left of these blue dots is your bodies of the cases. So if I connect this to case 0, then I basically will have A plus B right there. Now A and B, maybe there's a gate you can use for that, and if I AND them together, I connect this body into this case of 0, 1 to be forwarded, then I basically have A and B. 1, 0, maybe I can not it and connect to the third case, and pass A means actually do nothing. So maybe I could do pass A for you guys because that's easy. Let's see. Oh, whoops, there you have it. So actually here, I think we just connect our A into this last bit. Oh, of course, the bit size needs to be 8. And if I select 1, 1, case 11, I just get my A here. So it's your guys' job to do A plus B, A and B, A not A. Remember, multiplexer all it does is basically forwards it, so that's why I like to think of a switch statement. A switch statement basically forwards a single case in. And the same thing with intermediate bit ALU, except the little bodies that you're going to be implementing are going to be a lot more complicated. Like we have is double, is divisible by 16, multiplied by 9, and maximum. And this type of stuff you definitely want to know, especially for the time lab. You need to be comfortable with doing a little bit more complicated bodies. But the multiplexer part is hopefully that's simple. What I would do is I would click on circuits. I'd do new circuits. I'd rename this to is double. I think that was looks like it said is double. But I can start using our input pins here. So it looks like it is double between A and B is what it's guessing. It's trying to get it. I'll make these 8 bits. And the output is it's an 8-bit output, but I believe it's actually should just be a Boolean. We just have it 8 bits to keep it consistent with like multiply by 9, which is not a Boolean. And then so what that means is like even though it's 8 bits, make this less. The only bit we really care about is this first bit. So you figure out if A is the double of B, and oh, of course label them, makes it easy. A is double B. You implement your logic here. Maybe, and you can use any of the circuits you made before. You can even use, maybe the adders might help. And then these ones should be zeroed out forever because it's only a Boolean. It should be either true or false. So connect your answer for this 0th pin there. And then once I do that, I can actually start using my is double here. Fix the selector bits. I'll connect that to the 0th case. So this is the approach here. This keeps it organized. You don't really have to do the sub-circuit thing, but definitely keep it organized. And everything else should connect to output. Yep, so hopefully this helps a little bit. This is definitely going to take most of your time for this entire homework. But definitely reach out and ed discussion if you're struggling a bit. I know maximum is super hard. Like I remember from last semester, maximum and minimum has a lot of edge cases you gotta worry about, especially since we also have negative numbers to deal with. Oh yeah, make sure you're interpreting these as 2's complement. These are actually negatives. That makes maximum a lot harder. Trust me. All right, good luck.